So here we're going to talk about lines. So here we have a line, and on this line we're going to mark off 2 points with an ordered pair. We're going to call the first one x1, y1, the second one x2, y2. And we're also going to mark off the horizontal change with a delta x and the vertical change between those 2 points with a delta y. And we're going to use those to define a very important constant for a given line called the slope. The slope of a line, we're going to label it with a lowercase m. My lowercase m just looks like a small capital M. That's a lowercase m. And the slope is going to be defined as the amount of vertical change for a given unit of horizontal change. And of course, we can use division to figure that out. The amount of vertical change for a given unit of horizontal change, well then the slope is going to be the vertical change divided by the horizontal change. So delta y over delta x. Delta y, the vertical change, delta x, the horizontal change. And given 2 points on the line, delta y would just be given by one of the y values minus the other. So we'll take y2 as the one y value, y1 is the other, divided by the same change in x, x2 minus x1. And for a given line, this fraction is going to be constant, no matter which 2 points you choose on the line. So let's, well, in calculus, one of the most important things in calculus actually is concerned with slopes of certain lines given functions. We'll see that next week. But for now, let's get used to slope this way. Example, find the slope of the line containing the points 3, -2, and -5, 1. So right here we have 2 points. There's a line connecting 2 points. We want the slope of the line. Well, we're just going to use this change in y divided by the change in x. So slope, m, equals the change in y divided by the change in x. Just because this one is written second does not mean you have to interpret that as the x2, y2. You can use either one of these first, because a negative divided by a negative is a positive. So when I'm doing this, I usually just take the first one, change in y, -2 minus 1, divided by change in x, 3 minus -5, also known as 3 plus 5. So this slope is what? -3 on top, 8 on the bottom. So the slope is -3/8. Now, we chose 2 points on the line. We could describe a line by taking a given point and letting this second point vary across the line. So fix a point, and the line will be defined by that fixed point and a variable point that travels anywhere along the line. And that's actually going to give us a description of a line in terms of variables x and y. So let's write this as a remark. Remark. I'm not going to write this, well, that's a pretty long sentence. Letting x2, y2 vary in the slope equation, so let's say letting x2, y2 vary, we find what is known as the point-slope form of the line. Point-slope form of a line. And I'm going to write this in 2 ways. The second way will be the more common way. I'm going to write it once, then I'm going to erase it, then I'm going to write the other one. Maybe I won't erase it. I don't know. Let's see. Letting the 1 point vary, so letting them be variables in the line, we get this equation for slope. Slope equals variable y minus y1 over variable x minus x2. It gives us, I'm calling this the point-slope form of the line, but this way it is technically written is not the point-slope form of the line. The point-slope form of the line is this equation written in a single line, meaning get rid of this fraction. So multiply both sides by this fraction to get rid of the fraction, and it gives us what you are more familiar with as the point-slope form of the line. Y minus y1. So I multiplied by the denominator, and then I put this on the other side. So y minus y1 equals m times x minus x1. So I'm going to erase this first one. This point-slope form of the line is very important. Having this naturally, being ready to use this will be very important throughout a lot of calculus, in particular weeks 2 and 3. And the point-slope form, when I first saw it, I guess I didn't realize it was the same as the slope form, or the slope equation. But once I realized it was the same as the slope equation, without being written as a fraction, I realized it was a much more convenient way of describing lines than, say, a slope-intercept form. If you want a slope-intercept form, you'd add y1 to both sides, solve that for y. We won't use slope-intercept very frequently. So let's do this next one. I'm going to just erase this example a little. Find an equation for the line containing those points. So find an equation for the line containing these points. Well, I'm going to erase this, even though we need it in a moment. When you have the point-slope form of the line, all you need to find an equation for the line are a point and a slope. Here we have 2 points. Whenever in calculus I'm asked to find an equation for a line, whenever in Calc 1, let's say, I'm asked to find an equation for a line, I immediately think point and slope. That's all we need. We will see later in the semester finding this slope is something we can use calculus to find pretty easily. And you'll largely be given points. And one thing we will be doing is finding equations for lines. When we do that, we'll need a point and a slope. Here we're given 2 points. You can choose whichever one you want. I'll choose that one. And we need the slope. Well, we found the slope in the previous example. What was it? I wrote the second one backwards. You don't want to do that, because then your answer will be wrong. Be off by a negative. So we have the point, we have the slope, and that's all we need to find an equation for the line. So I'm going to write the equation over here. Equation, EQN, y minus the y value, so y minus -2, equals slope, which is -3/8, times x minus the x value. And you don't need to simplify that into slope-intercept form. You leave that as it is. That's a perfectly fine equation for a line. And you know it's perfectly fine because that rhymed. So we need an equation for a line, point and slope. Among the most important things you can do in calculus. 10 years from now, if you think of Calc 1, think point and slope. You might also want to think about derivatives, which are next week, or limits, which are this week. But an equation for a line, all you need are 2 things, a point and a slope. And then you need to put them in the right form. So for now, that's all we'll do with regarding lines. Let's talk a little about polynomials. The definition of a polynomial is a little complicated. I'm going to write it anyway. So we'll say f of x equals a n x to the n plus a n minus 1, x to the n minus 1 plus through a, let's say 2x squared plus a 1x plus a 0 is a polynomial with degree n. So what we have here, notice if all of these, well, let's say first, these a values, an minus 1, and so on, are all coefficients. They're all real numbers. X here, notice, is our variable. So a polynomial is number times x to something plus number times x to something else, and so on, down to number times x plus another number, is a polynomial with degree n meaning the largest non-zero term. And just an example. Example 5x to the 7th plus 9x to the 4th plus 6x squared minus 5x plus 1 is a polynomial with degree, that says degree. Degree is the largest exponent, in this case 7. Notice, we go from exponent 7 to 4 to 2 to 1 to 0. These middle terms can have coefficients of 0. So in this case, a 7 would be 5, a 6 would be 0, a 5 would be 0, a 4 would be 9, a 3 would be 0, a 2 would be 6, a 1 would be negative 5, and a 0 would be positive 1. We won't talk too much about polynomials in general. We will do a little bit with them in general. But for now, we're going to focus on degree 1 and degree 2 polynomials. Well, we've already focused on degree 1 polynomials. Degree 1 polynomials are in that form, which is the form of a line. And we'll see that a little more. We didn't see that directly in that line discussion, but it's not too important for now. We'll see that a few times throughout the semester, though. A degree 2 polynomial, meaning 1 written like that, is known as a quadratic function. So let's talk about quadratic functions. These will be very important throughout the semester. Quadratic functions. And I'll just write it as a parenthetical, a, k, a, degree 2 polynomials. Degree 2 polynomials. We will do a few things with these. Let's look at 2 of them. Let's look at 2 things we can do with these. Example, sketch a graph of this function. I'm going to write this on board 1 because we're going to use graph transformations. X squared minus 4x plus 9. Now, the way this is written, we can't immediately apply graph transformations. But notice, this has an x squared term. And what we're going to do is make this look like an x squared function with graph transformations applied to it. This was the first example of the 6 functions. And how are we going to do this? How are we going to make it look like x squared with graph transformations applied? Well, we're going to complete the square. And how are we going to do that? Well, completing the square is a process. And to start that process, I like to look at these first 2 terms. Well, I like to rewrite them, I guess. And ignore the 9 for now. We're going to need it eventually. But what we do here, looking at the x squared and the x, if the coefficient on x squared is 1, which it will be, all we have to do is look at this number here, which is negative 4. So we look at the coefficient on x, negative 4. Okay, there's negative 4. What we do with that is we take half of it, so divide by 2. And then, those are parentheses, not absolute values, and I guess although it's the same. So we take this, they're not the same in general. They're the same since I threw a square on. We take this negative 4, divide it into 2, and then we square that number. So what is this? Well, negative 4 divided by 2 is negative 2. We want to square that, which makes a positive 4. Well, okay. We look at this number, take half of it and square it, gives us a positive 4, and we put that there. Well, we can't just change the problem. I mean, we used an equal sign here, so we need it to be equal. Well, how can we make it equal? Well, the only number you can add to something and preserve equality is 0. So we're going to actually add a 0, but we need this 4, as we'll see eventually. So what we're going to do is add a 4 and subtract a 4, because that's adding 0. And then we're going to remember that 9. So we took this, we looked at this middle term, we took half of it and squared it, we added it, we subtracted it because we need to add 0, and then we left the 9 there. Well, now we can write this as a perfect square, because this piece right here factors into a perfect square. Which one? Well, this one. Those 3 terms that are underlined can be condensed as that square. Where did that negative 2 come from? Well, that number in there. So we condensed those as a perfect square, and then we just have to write these other 2 numbers. Well, I mean, not write them, we need to combine them. 9 and negative 4 make a positive 5. Well, right now, this is written in a form which looks like x squared with some graph transformations applied to it. So let's sketch a graph of this original function that we wanted using it written in that form. I'm going to erase all these number lines, or not number lines, underlines. So let's start, I'm going to start here with x squared. So here's x squared, f of x equals x squared. And I mark the point 0, 0 off on them. And what do? Well, we look at what happens to x. The first thing that happens to x is this negative 2. So we have 0 squared is 0, but if we have an x minus 2 squared, well, x equals 2 will cause this inside to be 0 squared like that. So this point 0, 0 is going to move over to 2, 0. And we drag the rest of the function along with it. Alternatively, it's a rightward shift of 2 units. Well, and then what do we have? Well, we have this positive 5 to deal with, and it takes all of these points and lifts them up 5 units. So this point 2, 0 is now going to be at, well, instead of 2, 0, it's going to go up 5 units, so 2, 5. And the rest of the function goes along with it. So given any degree 2 polynomial, any quadratic function, we can complete the square and then use that. Well, we can complete the square and rewrite the function in a form on which we can see the graph transformations. Let's do one more thing with degree 2 polynomials. But to do that, we need a definition. Yes, we need just one definition. It's a very important definition. It'll show up all 4 weeks. Maybe not the 4th week. Definitely, it'll show up in all of the first 3 weeks. Maybe I'll erase that too. So definition. We're using this definition in this quadratic section, but it applies in general to general functions. So x0, x sub 0, is called a root or a 0. I like root more than 0. Of f of x if f evaluated at x0 equals 0. So x0 is a root if f of x equals, or x0 is a root if f of x0 is equal to exactly 0. Well, in the graph we can see where that happens by looking at where the function goes to height 0, meaning where the function stays on the x-axis. We could also figure these out algebraically, so let's do a couple examples. Example, find the roots of these quadratic functions. So of, where do I want to write these? Let's just write them here. F of x equals x squared minus 4x plus 3, and f of x equals, maybe I'll write this over here, and f of x equals x squared minus 3x minus 10. So we want to find the roots of these two functions. Let's start with the first function, because it's first. Find the roots. Well, what is a root? A root is an x value where the function evaluates to 0. So what we need to find is where this function equals 0. So let's set it equal to 0 and solve for x. Well, with a quadratic, we can hopefully factor the quadratic so that we have two things multiplied equal 0. Because when two things are multiplied and they get to 0, one of them has to be 0. Well, can we factor this? Yes, we can. How can we factor it? Well, we need numbers. Well, we need two numbers which make a positive 3 and make a negative 4. Well, positive 3 and positive 1 make a positive 3, but they don't make a negative 4. However, negative 3 and negative 1 make a positive 3. Negative 3 and negative 1 make a negative 4. So we can factor this using a negative 3 and a negative 1. X minus 1 times x minus 3 equals 0. You can see what? Negative 3 times negative 1 gives you that. And then negative 3 plus negative 1 gives you that. Two things multiplied equals 0. You set each one equal to 0. So you get x equals 1 or x equals 3. This first thing equals 0 when x equals 1. The second thing equals 0 when x equals 3. Well, and let's do the same thing with this. X squared minus 3x minus 10. Again, we want to set it equal to 0. We're going to hope it factors because I'm not covering the quadratic formula, whatever that is. In a 4-week class, I'm going to skip over quadratic formula. It does not show up much in calculus. So we need numbers which what? Multiply to negative 10 and add to negative 3. Well, 10 and 1 make 10, but 10 and 1 don't make 3. 5 and 2, you can use a 5 and a 2 and make a 10. You can use a 5 and a 2 and make a 3. Do the negatives work out well? Well, to make a negative 3 with a 5 and a 2, we would need a negative 5 and a positive 2. And negative 5 and positive 2 make a negative 3. Negative 5 and positive 2 make a negative 10. So we can factor this as x minus 5 and x plus 2 equals 0. So these two make a 10, and these two make a negative 3. So two things multiply equals 0. One of them has to be 0. So you get x from the first one. X equals 5 will make that 0. And on the second one, x equals negative 2 will make that 0. And we'll deal with this type of equation many times throughout the semester. We'll see that. You might be wondering, in these two examples, the coefficient on x squared is a 1 in both of them. For the most part, I'll say probably between 80 and 90% of the time we have to solve these, the coefficient on the first number is going to be a 1. The other 10 to 20% of the time, the coefficient on the first one will be a prime number, like 2 or 3 or 7 or 5 or something. And I'm not going to ask anything where it eventually turns into like an 8 in front of them. That's, I mean, the type of thing you have to go through for that is not very useful in calculus. So I try to avoid it. I also don't really like having to think like 8x squared, because you can make 8. You can make an 8 and a 1, a 4 and a 2. I guess that's it. But in general, your coefficient is going to be 1. There will probably be 2 or 3 times where I throw like a 7 on there or a 5. Because a 7 or a 5, since it's prime, does restrict the choices a little. But you're not going to have like a 16x squared or 12x squared or something like that. And I don't want to have to do those, so I, of course, wouldn't want you to have to do them. So we talked about degree 2 polynomials. We will see degree 3, degree 4, and so on throughout the semester. We won't do as much with them, but they will show up. But for now, let's just set a little more of the language we need with functions. Definition. Definition. A rational function has the form p of x divided by q of x, where p and q, sometimes I don't write the of x when it's implied. So where p and q are polynomials and q is not 0. I mean, we're dividing, so we can't have the bottom be 0. A rational function is a polynomial divided by a polynomial. A rational number, some of you might know this. When I took calculus, I didn't know this. A rational number is just a fraction. Well, a fraction with whole numbers in the top and the bottom. A reduced fraction by some definitions. So a rational function is a fraction of polynomials. You can think of it like that, where the bottom is not 0. The domain of a rational function is just everywhere where the denominator is not 0. So if you have like x to the 5th plus 5, x plus 6 on top, and then you have x minus 2 on the bottom, the domain is everything but 2, because 2 is where the bottom would be 0. That'll show up a little, and we'll talk about it in a little more detail as we need it. Definition. A root function is of the form x to the 1 over n, where n is an integer greater than 1. A root function, so like x to the 1/5, x to the 1/2, x to the 1/3, and so on. They're all known as root functions. I mean, you could combine rational and root functions and create other functions. We'll do that at some point. We'll talk about domains of root functions a little as they show up. Well, we'll see. Not now. Another definition, I'll just describe this a little informally. Definition, an algebraic function let's say, involves the algebraic operations, so plus, negative, multiplication, division, rational powers. So you know root functions, and also if that numerator is some other number. Rational powers and roots. An algebraic a function is one which involves these, and you can combine or add or multiply, divide any of them, and so on. And a transcendental function cannot be described using the standard algebraic operations. So it's really one which is not algebraic. So I'll say cannot be described by basic algebraic operations. Some examples of transcendental functions: trig functions, exponential functions, and logarithm functions. All functions we will talk about in a moment are transcendental. They can't be described with the algebraic operations. So ones which can: rational functions, polynomials that are algebraic on root functions. The addition of those are all algebraic. Transcendental functions, trig functions, exponential functions, logarithms, and more. But those are the ones we will talk about today.